Okay, so I apologize, but as it turns out, I will not be here Tuesday and possibly Wednesday. So I'm going to be recording these lectures now and posting them online for everybody to see. I will be here Thursday. Thursday will be a work day. And please come in, or if you want to chat, let me know. We can set that up. So yeah, I'm going to talk a little bit about the project first off, and then I'm going to jump right into some more details, important details to know, especially when you're talking about C++. So anyway, for the project that's due this coming Saturday, the hardest part about parallelizing this correctly is getting the RMS correct. Doing it incorrectly can result in inconsistent behavior. Sometimes it hangs, sometimes it doesn't, sometimes it runs, sometimes it doesn't. Sometimes you just get a wrong answer, sometimes it just stops randomly. It's a pain in the butt. But what I have here is kind of a basic idea of how this, how your Jacobi program would work in parallel. Okay, so we have our main function here. We set some stuff up, and then we have a while loop. We say while RMS is, that should be greater than, I got that backwards. Let's change that, greater than 1 to the negative 13. All right, so I guess in here somewhere we've said some really big number. Okay, so it's bigger than 10 to the minus 13. And then we have our Jacobi algorithm, and inside this loop we calculate the RMS somehow. Okay, and this is just your basic equation for the RMS. And I think I actually did that one wrong too, now that I'm looking at it. Yes, keep them. The sum goes here. Square root goes there. Okay, so that's better. All right, so we calculate the RMS, and of course we jump back up to the top and we check the condition. Is it still greater than 10 to the minus 13? If it is, we keep going. If it's not, we get out of it. Now, parallelizing this is kind of the big problem, because if you, there's a lot of ways to do this, but if you write your parallel loop here, oh gosh. So if you write the parallel statement here, so, and we set up the RMS, for now I'm going to assume it's a shared variable. So we set up the RMS. At this point, once we hit the parallel region, all bets are off in that we do not know where each thread is located. So let's say, for instance, that the first thread gets through, he checks the condition, he makes it into the while loop. At which point, let's say you now have RMS. We have to set that to 0 so we can start summing it up. All right, and so it gets in here, it checks the RMS, it gets in here and then it sets the RMS to 0, but the second guy is still, he hasn't made it out yet. So he comes in and checks the RMS and says, hey, guess what? The RMS is equal to 0. And at that point, he jumps to the end. And your program hangs because the first guy is in here waiting for the second guy to show up. Okay? And so that, I ran into that problem when I was doing this project, and I've had a couple students already run into this problem. And you have to keep that in mind. And so you have to address that somehow, either using a barrier or you also have to remember your critical regions and a single region. Don't use a master. Another important thing to note is that a critical region, if we have our critical region here, so if we have 4 threads that all hit this critical region, the first guy, he hits it, he runs it, everyone else stops and waits. Okay? He finishes, but then he keeps going. That's important to remember. He keeps going. So once he reaches the end, the second guy starts going through. But if they're both trying to update the RMS, and so this guy makes it to the bottom, jumps to the top, sets the RMS equal to 0, while this guy is setting the RMS to something else, you got a data race condition. They're both trying to update the RMS value at the same time. Alrighty, so that's the big thing to note and watch out for. I hope I've explained that well enough. So if you have questions on that, please let me know. I will be available by email, just so everyone knows. All right, now I gave this short little lecture to a couple of students, and I thought it would be useful for everyone to know. I want to try and draw out the big picture of how computer memory works, because I haven't talked a lot about memory. Memory is the limiting factor in everything we do. So let's say here is your CPU, okay, and then we have our RAM, and then we have, say, the hard drive. Okay, and these components are all connected to each other through the motherboard. Now, in the CPU, we have registers. Registers are used to store values that are currently being operated on. We're adding 2 numbers together, and those will go in the registers. There's usually a very small number of registers. Along with this, we have the cache. And the cache is used to store values that could be used very soon. All right. So now let's say, okay, so now that those are kind of the main components of our hardware components, I should say. Now let's say you have a program. Your program is stored on the hard drive, okay, and you run this program. The instructions for this program get loaded into RAM and the cache. And by loaded, literally the data is copied from one place to the other. Now along with that, your program is going to need memory. All right, and the memory, I should say the operating system allocates in the RAM a certain amount. Actually, let's draw it this way. Allocates a certain amount of memory called the stack. All right, so this is your stack. And anytime you have, say, an integer A, double B, these variables are specifically stored on the stack. And it's called a stack because it's kind of a first come, first serve kind of thing. So integer A, since it's first, it gets put on the stack. Double B then gets stacked on top of it. If you go into a function in your program and you have some arguments, C and D, those get then stacked on top, C and D. And if you have, say, another integer in here, integer E, it gets stacked on top. All right? And the stack, the size of the stack is determined by your operating system, your compiler. It's kind of a mess, and we don't really want to have to worry about it. All right? And you will run into problems if you exceed the size of that stack. And so you get literally a stack overflow error. But oftentimes it shows up as a seg fault or a corrupted stack error. So anyway, that's important to know. Now, stack memory is generally faster than other types of memory because of the stack pointer. So your program always has a stack pointer associated with it. And what it does is it points to the top of the stack. And so if we're in this function, the top of the stack is where this integer E is, let's say. And when we exit that function, the memory isn't actually deleted or changes value. All we do is we move the stack pointer back down to where the main function was. And so it moves from here to here when we exit the function. The variables C, D, and E are still there. It's just that we no longer see them, in a sense. And because of the way the stack is set up like this, it operates very efficiently. You as the programmer, you don't need to worry about the stack pointer. What you do need to worry about is running out of stack, or but that's actually pretty hard to do nowadays with our big machines. So just so everyone knows, that's what the stack is. If you hear about it, that's what they're talking about. Now, every time in your program you have, say, a memory allocation. So every time you have a memory allocation where we do, let's do a different color. We do new, double, we want 100 doubles, and we store that into a pointer. All right, first off, the pointer itself is stored on the stack. The memory the pointer points to is stored somewhere else. The rest is called the heap. It's stored on the heap. And so we have 100 doubles in here. Now, so now your program wants to operate on, say, A20. All right, so what the program does is it says, all right, what memory address is the pointer A pointing to? Which the pointer is always pointing to the start, or A0. At that point, it then adds 20 doubles to figure out where A20 is. Unfortunately, well, not unfortunately, but it's just the way it works. Black. Can I not get black? Sorry, it's being dumb here. There we go. Okay. So A20 here, let's say that's 20, is part of this particular cache line. All right. So when we need to operate on A20, it doesn't just pull, it doesn't copy A20. It actually copies the entire cache line over to the cache. And the cache lines, they're kind of arbitrary, depend a lot on the hardware, but generally they are roughly 64 bytes in length, so it would be 8 doubles that would be in one cache line. So it's actually getting 8 of these things and storing them in the cache, at which point then A20 gets pulled into a register, it gets used. After it's used, A20 gets copied back to the cache, and if A20 needs to be used again, then maybe it won't evict it from the cache to memory. It'll keep it in cache and it'll keep reusing it until it is done with it. And then at that point, it sends it back to the RAM. And I should say it doesn't physically move, it copies the value. So if say A20 is storing a 4, and in the cache we have a 2, and in the register we have a 3, you can see that we're getting three different definitions of what A20 is supposed to be. And the hardware is supposed to take care of that. And so when it's done with it, it copies the 3 back to the cache, it copies that 3, and the entire cache line, it evicts the entire cache line back to main memory. And so now we have our 3 over here. Right? So that is kind of a basic idea of how memory moves through the system as your program runs, and the differences between all these cache lines and how they actually work. And I hope that helps a general understanding of what I've been talking about this whole time. So anyway, now we get to come to the fun part. So the fun part here is when you're dealing with a ccNUMA system, such as CHPC's hardware, whenever we allocate memory for a class, so if we have some class and we want to allocate some memory, like that, there's 2 things that happen when we call the operator new. First off, memory is requested from the operating system. And that's your allocation. And then the default constructor is called. And if we allocated an array of these things, the default constructor would be called on all of them. Note that the default constructor is not called for primitive types, unless of course you're using a standard library container, such as a vector or a list. And this causes headaches when you're using a ccNUMA system because of the first touch policy, which basically says you allocate some memory, and then whichever process touches it first, writes to it first, the memory will then be stored in that locality domain, as I talked about in a previous class. And since we generally don't want every thread allocating its own stuff, then the one thread that is running the new command is the one that gets all of the memory, which is not what we want. So here is an example from the book. Again, so this is actually in chapter 8. They have a class, they call it capital D, and literally all it is a wrapper around a double with a lowercase d. And they have a default constructor here. The default constructor takes a double, which defaults to 0 if nothing is given, and then initializes the private variable d to the underscore d. All right. So their example is that if we say by doing this on our dumb little class here, we have called the default constructor on all 100 of our doubles. They're supposed to just be plain old doubles. And so the whole thing gets initialized to 0. And since, say, the master thread was the one doing the allocation, then he gets all of the memory because he's the one that touched it first. So there are some ways around this. The first way is don't let the default constructor initialize the memory. So if we had written our default constructor without this or this, it wouldn't have touched the memory at all because it's not doing anything with it. So that's kind of the easiest way. However, this goes against all recommended C++ programming practices. The default constructor is supposed to set up your object to be in a default state. And if it's not, then undefined things can happen. And sometimes, of course, it's just not possible, especially when you're working with other libraries or other types. Another thing they talk about in the book is using the placement new syntax. This is something I actually didn't know about till a year ago or so. It's advanced, it's tedious, it's not really what we want to do. But it would work. All right, and so the kind of the middle ground here is to overload operator new. And so you can define a new operator for your class. And so when you say this, the compiler will then use your version that you have defined. Another option that the book didn't talk about, but that I thought of, is you could have each thread allocate its own memory. That is perfectly okay. But then you have to manage the memory. And OpenMP tries to make it so you don't have to do that, but C++ just screws everything up. You don't have these problems in Fortran. Just do everything in Fortran, people. Okay. So the job of an overloaded new operator is to allocate memory and return a pointer to it. After that, the default constructor is called automatically for each object. So here's an example for our D class. You'll see it returns a void pointer, which is correct. New is always supposed to return a void pointer. New is also supposed to throw some exceptions, but they didn't put that in here. So if you want to be technically correct, you have to do all that fun stuff and follow the standard. But the new, especially the array operator here, takes in a size underscore t parameter. Now, before you go off your rocker, just think of size t as being an integer. Okay, don't worry about it. It's just what it is. It's an integer. And it's an integer indicating the number of bytes to allocate. All right. So this new operator doesn't deal with D specifically. It deals with bytes. And so the way we're going to do this is we're actually going to allocate that number of bytes using a character. And a character is, generally speaking, 1 byte. And so now we have this character array of bytes, at which point we can then use OpenMP to properly allocate each section of memory between everybody. So we loop through, so we have our parallel 4. We're going to privatize J, which I don't know why they did that. They could have just thrown an integer in here. Int J would have done the trick too. The schedule runtime, this specifies that the type of scheduling is done at runtime. I'm going to talk about that in the next lecture. Generally, you're just going to use static. Another important thing to note, size of D. This returns the number of bytes of class D. Okay? So size of D, that's what it does. Number of bytes of class D. So basically, since we now have, let me draw our memory here. So this is every single byte of memory, but a double takes up 8 bytes. Okay, so the size of D in this case is 8. So this would be one double. And we want this entire double, this entire object to fit inside of, or be owned completely by one thread. So we have this outer loop here that loops from 0 to n, so it loops through the entire array, but it does it in chunks. Oh, dumb PowerPoint capitalizing things. It does it in chunks of 8. Okay, so it basically skips from here to here to here. And then we have an inner loop that loops from 0 to size of D. And we set pi plus j equal to 0. And so the inner loop starts here and says, that's 0, 0, 0, 0, 0, 0, 0, 0. At which point the outer loop then jumps to here. So we've now initialized that entire space for the double to 0. And really all we're doing is we're touching it. We want each process to touch that space of memory that they will end up using. And so then the next guy, anyway, so then the next guy goes and the outer loop starts here, and the inner loop sets each byte to 0. At which point we then return P. After this, the compiler will call the default constructor automatically for each object, but the memory has already been touched, it's already been separated amongst the threads. And so that's kind of the easiest way to get around that. All right, so problems with standard vector. By default, standard vector default initializes its data when it's allocated, even for the basic types. And so basically when it allocates it, it touches it. And we basically come back to the same problem we had before. Thankfully, all the standard containers have a template parameter known as an allocator. Now, an allocator is a class that is designed to allocate memory. Excuse me. And they have to follow a specific format. Excuse me again. They have to follow a specific format. And I'm not going to go into details about this because it's a complicated topic. But listing 8.1 in chapter 8 gives an example of this. And you see it's really long, and that's why we're not going to go over it. All right, for our class, you can just use plain old boring arrays. You don't have to use standard vectors. Anyway, the ccNUMA aware allocator, or the OpenMP aware allocator, will then allocate the data, initialize it in parallel, so that everybody gets their own piece of the pie. Right? Here's another problem. Pushback. Pushback is like one of the greatest things ever with standard vector. A vector is supposed to be kind of a programmer-friendly dynamic array. Normally, without that, we'd have to calculate how much data we have, we'd have to allocate the memory, then we'd have to copy the memory in. Instead, we have the pushback, where pushback says, I don't know how big I am, but we'll just keep popping values in here until we have the right amount. So the way it does this is it allocates more memory than it needs. This is called the capacity. Once the capacity is reached, so let's say it allocates to be this big, and we push back numbers until we get to the end, at which point it allocates new memory that is bigger. It copies the old values in and pushes back the new one. Okay? And so once the capacity is reached, we allocate this memory and it's default initialized. We copy in the old ones and we push back the new one, the new value, and then the size of the vector is incremented by 1. Even with the parallel allocator, at that point it would kind of be a guessing game for us to know which processor has what data. And it completely ruins our scalability, our ability to work with the hardware. So the moral of the story is don't use pushback. Okay? Use resize, the resize function, to resize it to the size you need and go from there. And that is the end of that presentation. In short, just use Fortran. Don't have these problems. Gee whiz. But those are things to be aware of if you want to do serious programming with C++ and parallelize with OpenMP. Next week, we're actually going to get started on MPI, which doesn't really have these problems. So you can just avoid it by using MPI. And in a lot of ways, I feel like using MPI is easier because you don't have all these technical issues. So that is the end of this lecture. And email me with any questions you have. I will address them. I will put things on Canvas if I need to. I am here for you. So thank you for watching.